that as well. So okay, so we've got a backup system. We've got a fail-safe system where we've got 2 recordings of the session taking place. So I'm just going to skip back to the slide I've just shown you. So armed with a basic understanding of Boolean logic and truth tables, which we did actually cover very quickly last week, we can actually determine such things as algorithms that correctly controls a cache memory or a BMW engine, or a system that allows an electronic game to be played, or in our case, and it's a very simple case, we're going to ask ourselves, what is the logic that enables us to calculate the result of 2 16-bit numbers? And we want to come to understand how by providing the Boolean logic of what's happening, we can move from the logic equations to hardware, real hardware. And you may have missed it, but I think several weeks ago, I actually showed you a device. I mean, I could actually, if you bear with me for 1 minute, I'm going to actually show you the device. But before I do that, I'm going to share a webcam. So the system's looking for the webcams, and I'm actually now going to share it. So you're actually seeing my table at the moment. But wait a moment. So what I'm about to show you is what's called a development board, and it's for hardware development. And let me see if I can get a better shot of that. This is the development board, and I've got lots of these at home. So if anyone would like one, you're welcome to it. And there's some quite impressive software to go with it. Let me just try and it's not going to be terribly well focused, I don't think. But what I've actually got here are 2 ports which I can use to connect to my laptop, and here right in the middle is what's called a programmable logic chip. In other words, it's a chip which I can program to perform a particular function, and if needs be, I can reprogram it. I mean, so it's got multiple uses, and it's very useful. And I've got all sorts of things, like I've got let me see, is this on? Let me just put the light. Oh dear, wait a minute. This light should be. I'm not sure why this light's not on, but still. Here I've got a bank of dip switches. Here I've got a little video display, so I can actually see what's happening here. And I've got a variable resistor to control various circuits. I've got all sorts of ports which I can connect to other systems. Here, like for example, I've got 2 USB ports, 3 USB ports, a power supply, and other circuitry. I've got some jumpers and so on. And what this means is that if I design a system, if I actually design a system on my laptop, and it could be like a controller, it could be a car's engine management system. I can actually download the program instructions onto this chip and make this chip do whatever I want to make it do. And this is quite an inexpensive development board. I mean, it doesn't cost very much to buy, but it's uh, it's great for developing your understanding of computers and computer science and hardware. And it does actually come with a big development system. I mean, it's a bit like Eclipse in terms of its complexity. I mean, you've got that fine control over what you're doing, and the language you use. Well, it's not Python and it's not Java. It's something called VHDL, and I'll mention that again a bit later on. Oh, so I'm so sorry you, you haven't seen any of that, have you? Um, I mean, I could. There's the board. I'm sorry, I forgot to show you the actual um, camera that I was actually not sharing the board with you. And there's the board. I'll just repeat the main points about that. I mean, I've got some various dip switches here. I've got a display here. I've got a lot of different connecting ports if I wanted to use them, including some USB port and so on and so on. And there's the power supply. And the main connections to my laptop will be using this USB port here. But I could, I can, um, and this is the main chip. It's what's called a Xilinx chip. It's quite a powerful little chip that's reprogrammable. You can change its function. So anyway, I'm happy to have at least shown you that, and apologies for not actually giving you the display straight away. Okay, so the key steps when it comes to designing a system is that you design the logic using uh, the logical operators and or and not and so on. And if you want to, you can optimize the logic by hand. Then you can map the operators and their interconnections to logic gates. I mean, we don't need a development board to do that. We can actually do that in a very straightforward fashion, which I will illustrate to you a bit later on. And then the connected the connected logic gates will provide the proposed or the intended functionality of the system that you've just designed. So I'm perhaps exaggerating things a little bit, but okay, Mustafa, I've just said you know these topics. Well, I'm not quite sure which topics you know about, but I'm just going to carry on ahead. And um, uh, the point of my demonstrating and talking about all this is that uh, within a few minutes you can actually produce working hardware which typically will be at least an order of magnitude faster than an equivalent software program running on your laptop. I mean, if you want to actually produce devices that have a particular functionality and are very fast, then you could do this. And the whole development process might take a couple of hours only. I mean, it's not as though you're going to have to wait months before you get some working hardware back. So let's just carry on because we're still on the overview stage. So one way of doing this is by rewriting the logic specification, which you've done using Boolean logic into a very high level hardware programming language, such as something called VHDL. So you know, if you wanted to, if you're interested, if you're open-minded, you might spend 5 minutes just looking at VHDL. And I think it's still used in quite a large way in I guess all over the world. But there are alternative ways of doing that now. And here I'm just showing you what the development system looks like. And what I have here is a VHDL program. So I'm representing Boolean logic and gates using this language. So it's called VHDL. And it's very flexible because I can choose the actual hardware device that I want to put the program onto. Or putting this another way, I can choose a particular chip for programming. I mean, it might be a big chip, might be a little chip, might be a very expensive chip, might be a very fast chip, and so on. And I've got control over all this. I can produce a lot of diagrams and statistics about what I've actually done. I can implement various constraints that I want to place on the system, and I've got a little clickable item here called implement the design, and that'll result in this program being converted into logic, into code that I can download to this chip, this Xilinx chip. Anyway, I think that's okay. So the second part of today's work addresses numbers having a specific number base, such as denary or decimal numbers with base 10. And we can come to understand what a decimal number means in terms of the sum of powers of the base, in this case the base 10. And this general idea extends to numbers in any other base, like base 16, or any n where n is an integer. So it's quite important to understand that. And we then consider how binary numbers can be effectively converted to decimal, and hexadecimal numbers, and vice versa. And we should, on our way, consider the whole point of using hexadecimal numbers in computer science in the first place. So we'll spend a minute considering that issue. Why do we use hexadecimal numbers? What's the point? What's the purpose? And it's the subsequent, so I think the final presentation, we first of all discuss the addition of two n-bit numbers and then create a small system that can calculate the result of 2 bits together. And from this we can obtain a 2-bit adder. And by further reflection of using a carry bit, for example, which is needed if we add binary 1 to binary 1. I mean, 1 plus 1 is actually 1, 0. So it's 0. The result of adding 1 to 1 is 0, but carry 1. Carry the binary bit 1. And we can come to understand how two n-bit numbers can be added together, whether these are 0 or 1. So hopefully, there's nothing too difficult, and in anything that I'm going to talk about, and hopefully it'll be of some interest. And the very last thing that we're going to do is to consider how a computer that does not offer a subtraction operator, and if you remember, Mustafa, the computer architecture that we looked at right at the beginning, or which you looked at from the beginning of the course, didn't have an instruction for subtraction. So the question is, well, what do? How can you actually perform subtraction on a computer that doesn't actually offer a little bit of hardware that does subtraction, or doesn't actually even have an instruction for subtraction? I mean, I think the computer architecture did have a decrement operation. You decrement a given number in the accumulator by one, and we had that, but nothing else. So I think that's probably quite enough for me to talk about. So I'm going to actually load up the first of my presentation, and I'm going to, I guess, talk about computer arithmetic. So here we go. So we're focusing on number basis, and you might know all this already, but others in the group might not. So that's the justification for looking at this. So the intended learning outcomes for this part of the session is that we're going to think about the function of bits and bytes, and then we're going to have a look to see how number bases actually work. And then we're going to think about conversion of binary numbers to decimal and vice versa. And then converting decimal numbers to hexadecimal and vice versa. So that's a fair amount of work to look at. So first bit of background I want to give you is that a bit really stands for binary digits. It's a shortened form of binary digit, BIT, a bit. And you can think of 0 as representing an off state and 1 for a non-state, or in terms of electrical signals you could think of a 0 as representing a particular voltage and 1 representing 3.5 volts, if you like, in a digital circuit. And either each binary digit has got to be 1 or 0. There's nothing in between. So it's either exactly one of the following holds. It's either a 1 or it's a 0. And strings of 1s and 0s can be constructed in order to represent any data that we can think of. And I defy you, Mohammed, to think of some data that cannot be represented by means of sequences of 1s and 0s. And we're probably familiar with the idea that you can represent text in terms of a binary sequence. I mean, maybe a sequence of 7 or 8 bits, and you can represent a sound by means of a sequence of bits. I mean, you will know from the work that we did a couple of weeks ago that you can sample a sound and represent the particular sound that was sampled by 8, 16, 32, 64 bits and so on. And you can represent video by means of binary sequences and so on. And such sequences can be transmitted within a computer. So we were talking about bits and their transmission between one computer device and another at a very high speed. I mean, it doesn't seem very high relative to possible speeds, current possible and future speeds of operation, but 2 billion bits per second if your computer has a fairly slow 2 gigahertz clock. And the obvious background that you need to be aware of is that a bit has 2 permutations, 1 or a 0. So a single bit can be in exactly one of 2 states. Therefore, 2 bits have 4 permutations, 1, 1, 1, 0, 0, 1 and 0, 0. 3 bits have 8 and so on. And n bits, so it should be lowercase n here, lowercase n bits has 2 raised to the power of n different permutations. And if you think about it, 4 bits would allow us to represent the English alphabet, 26 characters. 8 bits could represent 256 different numbers, so I can represent lots of different numbers using 8 bits. 10 bits I could represent 65536 permutations and 65536 different numbers. If I'm operating with 32 bits, I could code data using those 4 billion unique permutations. And a little bit more background. I don't know whether you've heard of these expressions, but they do exist, and it's a measurement of number of bytes expressed in terms of powers of 10. So a ki stands for kibibyte, and in fact 2 raised to the power of 10 bytes. And a mebibyte is 2 raised to the power of 20. And a gibibyte is 2 raised to the power of 30 bytes. And a tebibyte is 2 raised to, it's 2 raised to the power of 40 is actually an enormous decimal number. So kilobyte, 10 raised to the power of 3 bytes. A megabyte, 10 to the 6. Gigabyte, 10 to the 9. Terabyte, 10 to the power of 12. And there's something called an exabyte, which is a pretty big number of bytes. I'd like you to research that. What is an exabyte? What is an exabyte? How big is it? So, number bases are written just by using just by writing the base here as a subscript to the number. So here, 43 to the base of 10. Binary to the base 2. Hexadecimal number to the base of 16. And in the hexadecimal system, I was just looking at the news. Some event has just happened. Hexadecimal numbers use base 16, and we use digits 0 to 9, and then we use letters A to F. So for example, IE is actually 30 to base 10. 1E. And I can represent any hexadecimal number by means of 4 bits. So here are the first 4 bits. These bits represent the number 1. Here's the 1. And 11110, 1110 represents E, and it actually represents the number 14, I think. Yeah? So does that work out? Does that correspond to 30 decimal? I'll leave you to check that. So 111. What does 111 in binary? What is 11 in binary? It's 2 plus 4 plus 8 and 16. And 16 plus 8 is 30. Okay. So I can try, I'm giving the game away a little bit here. The hexadecimal number consisting of two hex numbers is equivalent to, I'm claiming is equivalent to 30. Well, you could rewrite 1 as the hex number 0001, and you write E as as the binary number 1110. Yeah. And if you now know how to convert that into a decimal number, it does give you 30. It's 2 plus 4 plus 8 plus 16. Yeah? So have a look at this representation of the decimal number 2096. Right? I can represent what this number actually means is looking at the first decimal digit 2. It's 2 times 10 raised to the power of 3. Right, 2 times 1,000. Then the next decimal digit 0 represents 0 times 10 raised to the power of 2, which is 100, which is 0. And the third decimal number 9 represents 9 times 10 raised to the power of 1, which is 9 times 10, which is 90. And 8 represents 8 times 2 raised to the power of 0, which is 8 times 1, which is 8. Here's the 8. So if somebody were to ask me how to understand a decimal number, I'd actually could show them by analysing this number into a sum of powers of 10. A sum of powers of 10. So 2 times 10 raised to the power of 3 plus 0 times 10 raised to the power of 2 plus 9 times 10 raised to the power of 1 plus 8 times 2 raised to the power of 0. And if you want to analyse the meaning of this binary number, so it's a number with base 2, you can similarly analyse it in terms of a sum of powers. And I reckon it's this 1 corresponds to 1 times 2 raised to the power of 7 plus 0, got a 0 here, 0 times 2 raised to the power of 6 plus 0 times 2 raised to the power of 5 plus 0 raised to the power of 4 plus 0 times 2 raised to the power of 8, 2 raised to the power of 3 plus 1 times 2 raised to the power of 2 plus 1 times 2 raised to the power of 0, which is 2, and 1 times 2 raised to the power of 0. And if you add all those, if you add 128 with 4 plus 2 plus 1, you get 132. Okay, so what I'm claiming, and you might not like this, you might not think it's the best way. What I'm saying is that if I analyse a number with a particular base in this way, as a sum of powers of the base, I can explain what a number to that base is. And similarly, this sort of analysis tells us what a binary number is. So each of these digits represents a particular power of 2, and this number, if I wanted it to convert it to decimal, all I have to do is to say it's 2 raised to the power 1 times 2 raised to the power of 7, and so on and so on and so on, and that'll give me the decimal equivalent. So what about what about decimal to hexadecimal conversion? So I'm sorry, I've missed out the letters DE here. So decimal to hexadecimal conversion. I'm giving you a rule for conversion, and it's an effective rule. And what we first of all, so we're going from decimal to hexadecimal. What we first of all do is to work out the binary equivalent of the decimal number. And we get 110100011. And and I'm going to show you how I get that, how I get the binary number using an effective rule as well. So I'm assuming that the binary equivalent of 211, sorry, the binary equivalent to the decimal number 211 is this. Well, that's the first thing I do. And what I can then do is to convert, sorry, what I can then do is to convert this binary number into two groups of 4 bytes. So here, look, here's the first 4 bits. This is the second 4 bits. So I'm just doing a splitting operation. I'm converting the binary equivalent of that decimal number into groups of uh, groups of 4 bits. 2 groups of 4 bits. Here's the first. There's the second. Okay, so the question is, let's have a look at 1101. Let's convert that into a decimal number, into a hexadecimal number. Well, it's actually D. It's the hexadecimal number D. Remember, E is going to be 1111, and D is actually going to be that number. I mean, convert that. I mean, supposing that was just 4 bits, so I've got 2 times 2 raised to the power of 0 plus 0 plus 1 times 2 times 2, so it's plus 4, so I've got 5 so far. And then 2 raised to the power of 3, that's 8. So 8 plus 4 is 12 in decimal, but in hexadecimal it's actually the number D. Okay, the second group of bits was 0011. So what I can do is to simply convert this sequence of 4 bits into hexadecimal. Well, it's actually, in binary, it's just 3, and that's a perfectly good hexadecimal number as well. So overall, our number, which is 211, will actually convert into D3, hexadecimal. So I hope you understand that. So a moment or two ago, I spoke about decimal to binary conversion, and I said I'd show you how to do that. And let me do that. Supposing I'm just giving you a rule for doing it. Supposing we wanted to convert 98 decimal into binary. Well, what I can do is to repeatedly divide 98 by 2. So dividing 98 by 2, I'll get 49 remainder 0. Dividing 49 by 2, I get 24 remainder 1. Dividing 24 by 2, I get 12 remainder 0. Divide 12 by 2, I get 6 remainder 0. And dividing 6 by 2, I get 3 remainder 0. And then dividing 3 by 2, I get 1 remainder 1. And finally, 1 divided by 2 is 0 remainder 1. So what I'm left with is just a sequence of remainders. In other words, it's having a look at this column, sorry, yes, having a look at this column, I'm actually getting 0, 1, 0, 0, 0, 1, 1. Well, that was quite easily done. But now, what I need to do is to reverse the series. I reverse this series, and what I get is 1, 1, 0, 0, 0, 1, 0. And that is the binary equivalent of 98. And if you wanted to, you could check that out. I mean, I think it's. I mean, I'm not. I think that's 64 plus 32. So that's 90. What did I say? 64 plus 32. That's 96. So, and add 2. This 1 stands for 2 raised to the power of 1, which is 2. Sorry, 2 raised to the power of 2 raised to the power of 1. And that should be equivalent to 98. So just check that for me. Just check that for me. So what I can do is to convert the decimal to binary by repeated division, reverse the sequence, and you get a number which, if you want to, and which you should do, is to check that this binary number is equivalent to the number that you had to convert. But there is a second rule which involves repeatedly subtracting the highest factor in terms of powers of 2 from the number until you get 0. Let me explain that. I mean, it's quite a nice method. And I'm sorry my diagram is a bit complicated. But in this rectangle here, I've written out the powers of 2. 2 raised to the power of 9 is 512. 2 raised to the power of 8 is 286. 128 is 2 raised to the power of 7. 64 is 2 raised to the power of 6. 2 raised to the power of 5 is 32. And 2 raised to the power of 4 is 16. Then 8, then 4, then 2, then 1, and so on. So what I can do, and here's a completely different example. What I want to do is to convert 363 decimal into binary. So let's use this second rule instead of the first rule. Let's try it out. Well, if you have a look at 363 and have a look at the decimal equivalents of all the powers here, it seems to me that you can't take 512 away because 363 is less than 512. But you could take 256 away. So let's do that. If you take 256 away from 363, you get 107. So what I've done here is to write a 1 here corresponding to 256, and then having a look at 107, well, and having a look at these decimal numbers, I can't take 128 from it, but I could subtract 64. I could do that. And if I do that, I'm left with 43. Alright, so I'll put a 101 here, because 1 corresponds to this 64 here, taking 64 away. 43, I could take 32 away, which is 2 raised to the power of 2 raised to the power of 5, and that gives me 11. So I reckon, I'm not quite sure. So, okay, there's a mistake here. That 0 shouldn't be there. This sequence should be 1, 0, 1, 1. I don't know what this 0 is doing here. I've marked it with a black vertical line. It shouldn't appear. So I'm looking at 11 now. And what I can do is, I can't take 16 away from it. I can take 8, which is 2 raised to the power of 3. And that gives me 3. So I'm going to mark, so So this has got a bit out of order, I'm afraid. So I'm taking 8, and then I guess I'm taking. Okay, I can't take 4, so I'm writing this 0 here. But I can then subtract 2, so I'm putting a 1 here, and I'm left with 3 minus 2 is 1. And I can take 1 from 1 to give me a 0. So I'm writing a 1 here corresponding to 2 raised to the power of 0. And so there is a mistake in this sequence, and I'm claiming it should be that. And I can check. So that's not going to. This is this is fast. I can work backwards. So the original number should be 256 plus 64 plus 32 plus 8 plus 0 plus 2 plus 1. Now, I don't know, you'll have to check, is that equivalent to 363? I mean, I've tried to check working backwards using the faulty sequence here, and I get 363. So I should have checked this. I mean, it should be 1011. 1011. I shouldn't have this 0 here. Can you check all that out and make sure you do understand what I'm doing here? I mean, try as a homework exercise. Just try converting 501 into binary. Do it. Just do it. Get some exercise. And so, how do you convert a hex number to a decimal number? Well, what you can do is to look at the hex digits in turn and convert each to binary, right? Convert each hex number to binary, and then it's going to be relatively easy to convert the resulting binary number to decimal. So as an example, what's 2A3 in decimal? Well, you can represent a hex number by 4 bits. Question I'm asking you is which decimal number is represented by 1111? And another question I'm asking you is how many hex numbers can be represented by n bits? Well, the answer to that question is 2 raised to the power of, you can represent 16, obviously 16 different numbers using 4 bits. And the smallest number will be 0, and the biggest number is 15. And 15 in hex is f, the number f. Okay, so each hex number is representable by 4 bits. There's no problem with that. So what we have to do, I'm giving you a table of equivalents. So 0 all the way up to 9, then an A. I've forgotten the B, of course. I can't write that in, so I should have actually put a B, C, D, E, and F. Those are the 16, 1, 2, 3, 4, 5, including B, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So using 4 bits, you can represent all these hex numbers. So we're converting a hex number to decimal, aren't we? 2A3, that was the number that we want to convert. Okay, well, I can represent this hex number too in binary by 0010. Hope you agree with that. And I can represent A in terms of 4 bits, these binary bits, which is 1010. Okay, so what is that? What number in binary is that? What is A in binary? Well, it's 8 plus 2. It's 8 plus 2. It's 10. And 10 is represented in hexadecimal by the character A. So that's okay. That's the first hexadecimal number after 9. Okay, so we've still got to convert 3, this hexadecimal number. Okay, well that translates fairly easily into 0011 in binary. So what we've got adding all 3 sequences together is this check it with me, 0010 followed by 1010 followed by 0011. And if you've got the patience of converting this binary number into decimal, you should get 675. And I think it's at this point I can raise the issue of why on earth do we bother with hexadecimal numbers? Why don't we work with pure binary numbers? Well, the situation we're in now makes it intuitively clear. Hamid, look at this number for 5 seconds. Can you memorize it? And in 5 seconds' time, will you be able to duplicate it? I mean, I think that's quite a difficult number to remember. And okay, maybe I could remember it for a fraction of a second. Or maybe I've got some memory technique that it does allow me to memorize 12 sequences of 12 binary bits. But I'd much prefer to remember the word as remember the number as the hex number 2A3. I can remember that. I can tell you what that is in 10 minutes' time if I have to. 2A3. It's much easier to remember than this complicated sequence. I mean, supposing I've got a number 2A3, which is going to be 24 bits long. It's actually going to be almost impossible to represent this, a sequence double this size. And yet, we're doing computer science, and as we know, a computer system works based on the use of binary numbers. You can store binary numbers. You can store a bit in a flip-flop. You can store a sequence of 8 bits in a register. It's all based on binary numbers, binary sequences, and even instructions are given a low-level binary representation. So I think you'll agree with me that a very good reason for using hexadecimal numbers is to do with surveyability or memorization, being able to memorize something. And what I'd like you to do, and time is very short, is to practice converting numbers from one base to another, decimal to binary, and so on and so on. And I remember when I was about 14 at school, we were always using numbers to the base of 13, and I used to think, why on earth are we using base 13? What's the problem? What's the point of doing that? But I can understand using binary numbers. numbers to the base of 2, and numbers to the base of 8, and numbers to the base of 16. I mean, there's a good reason for doing that. And that brings me to the conclusion of this second part of the presentation. So Mustafa, sorry. What is this? Oh, F. Yes. Yes, good. Excellent. Okay, you've got another method. Fine. I've given you a couple of methods for different sorts of conversion problem. I think you should be aware of the methods I've shown you, because at a university you might be expected to be conversant with these methods. Absolutely standard. You should always show your working as well. Whenever you're being given a question, say convert FAF into binary, you should show your working out. That's important. Very important. Okay, so I'm going to upload another presentation and get rid of that one, and we'll do a little bit of computer arithmetic. So it's computer arithmetic part 2. We're going to learn about 2's complement and the use of 2's complement numbers and subtraction. Use 2's complement numbers for subtraction. So I'm going to explain what a 2's complement number is and how you can actually convert a signed number into a 2's complement number. I'll show you the method for doing that. So what I'm doing now is to first of all show you something that's obvious to most people, how to add unsigned binary integers and to multiply unsigned binary integers. Then I'm going to explain 2's complement numbers and show you how to add and subtract using 2's complement. And remember, one good reason for understanding 2's complement numbers is that it enables us to perform subtraction in a computer system that doesn't actually give you subtraction hardware. Okay, so I'm going to just zoom through this fairly quickly, but you can stop me at any point. To add 2 unsigned binary numbers, you first line the 2 numbers up on the right hand margin. So these 2 numbers are aligned to a vertical line going down here. And I can simply start by adding 1 to 0, and the rule for binary addition in this case is that 1 plus 0 is 1, and 0 plus 1 is 1, and 0 and 0 is 0, and 1 and 1 is 1. Sorry, where are we? 1 and 1 is 1. So help me out. So I've lost concentration here. So 0 and 0 is 0. 1 and 1. Okay, 1 and 1 is 0 carry 1. And then 1 and 1 added to 1 is 1 carry 1. So I'm using, in this row, in this column here, I'm adding 1 to the carry 1. got 1 and 1, and 0 and 0, which gives me a 1, and then I'm adding a 0 and 1 to give me a 1. So hopefully that's quite clear. Those are the 4 sub-rules involving a carry bit. So if you add 1 and 1, you get 1, 0. You carry the 1 and put a 0. So that's a bit of a mess as well, isn't it? So a 1 and a 1 is a 1 and a 0, and a 1 and a 1 should be 1 and a 0. So I don't know. That's all we need to know. It's 3 rules. All right. Add 2 zeros, you get 0. Add a 0 and a 1, you get a 1. Add 2 1s, you've got 1, 0, because you're carrying the 1. Multiplication. Again, you align the 2 numbers to be multiplied up in this way. So I'm going to start with the rightmost one here. And so 1 and 1. It's ridiculous. 1 and 1. So 1 multiplied by 1 is 1. 1 multiplied by 1 is 1. 1 multiplied by 0 is 0. 1 multiplied by 1 is 1 here. 1 multiplied by 1 is 1. And taking the second binary digit, 1, and putting it an initial 0 here. 1, 1 is 1, 1, 1 is 1, 1, 0 is 0, 1, 1 is 1, and 1, 1 is 1. So now add 1 and 0 is 1, 1 and 1 is 0, carry 1, 1 and 0 is 1, add it 1, and you get 1, 0. And then adding a 1 and a 1 and a carry 1, you get a 1 and a 0, and then 1 and a 1, and add them to a carry 1 gives you I'm sure you'll be able to do this yourself. I'm finding it tricky keeping track of the cursor here. So let's just do that. 1 and in this column here, you're adding 1 and a 1, and you've got a carry bit. So you get a carry 1 and a 1, and then a 1 and a 1. Sorry, a 1 and a 0. So how come you're adding you've got a carry bit, so you're adding a 1 and a 1, which gives you a 1 and a 0. Oh, I thought this was going to be an absolute doddle to just explain this, but I'm just finding it slightly confusing showing you on the BBB screen. So, but hopefully that's very clear, and there's no real issues there at all. But I'm just reminding you. So 2's complement is a method to represent signed integers like minus n in binary. And this simply means that the positive and negative integers can be represented. And the purpose of this section is to show you how 2's complement can represent negative integers. So let's do it. Let's do it. And I'm going to use this, I'm using 8 bits for demonstration. And if you have a look at the most significant bit, I'm going to expressly use a bit here to represent. If you've got a 1 here, it means that the number starts with minus 128. So if I've got a 1 here and a 1 here, the actual number is going to be minus 128, plus 64. Right? So supposing we wish to represent the binary code in decimal using 2's complement. So I'm assuming that's a 2's complement number. You'll notice that the most significant bit is negative, and using an 8-bit code, the most significant bit has a value of minus 128. So, converting to decimal, converting to decimal to binary using 2's complement is slightly more difficult, as you'll be starting from a negative number and working forwards. Remember that if the binary number starts with a 1 in its most significant bit position, it's a negative number. So this number here, I'm going to use to represent minus 100. Well, how's that possible? Well, the first bit, minus 128, and then I've got a 16, and then I've got an 8, and then I've got a 4, and adding 16 and 8 and 4 together, and then subtracting 128, you do get minus 100. So I can represent, using binary code, an assigned number. Here I'm representing minus 100. So let's convert a decimal number, a negative decimal number, into binary. Well, first out you write the binary equivalent of 102. And starting at the least significant bit, you write out the number again until you come to the first occurrence of 1, and you flip all the remaining bits to get the number 100111010. And this number is now in 2's complement and represents minus 102. So so this is the result of flipping all the bits of the number after the first occurrence of 1. So have I actually shown you? Yeah, I've given. What's that number? So I've got. I'm just looking here. So this binary number here, where my cursor is now, represents plus 102. I mean, you can confirm that by just adding 64 and 32 and 16 and so on all together. What I do to convert it into a 2's complement number is, starting at the most significant bit side, which is 0, work your way left until you come to the first 1. Well, here's a 1. You leave that, but you flip all the other bits. Flip them. So here, instead of 1, you're going to get a 0, and here you're going to get a 1, and then another 1, then a 0, then a 0, and then a 1, which is exactly that. And this, interpreted as a 2's complement number, you can start adding minus 128 with all these, and add them together with these factors, and you should get 102. Minus 102. Minus 102. Sorry, you should get 102 back again. So check the latter. Minus 128 plus 16 plus 8 plus 2 is in fact minus 102. So notice one thing. Using 8 bits, we can represent the numbers in 2's complement from 1, if you had a 1 here and everything else was 0, you'd be representing minus 128. And if you put a 1 here and a 1 here, you'd actually get minus 127 and so on. So if you had a 1 here and all these were 1s, which number would you have? What is 60? Can somebody actually add 64 and 32, 16 and 8 and 4 and 2 and 1 together? Isn't it 127? Can you do that for me? Or is it 120? Yeah, 128. So what's, just do that. Let me do it. 60, that's 96, 106, 112, 120, 124, 126, 127. So if you had all ones, you could actually represent minus 1. Am I right? Okay. So starting from minus 128, I then move on to all the numbers I can represent with this as being a 0. So I've got 1, 1, 1, 1, 1, 1, 1. Okay, so I can represent all positive numbers from 0 up to 127. And there's 256 different numbers in total. Okay, so hopefully you'll look at this again and just check it out. If n bits are being used to represent unsigned binary values, the greatest value would be 2n minus 1. So where n is 8, the largest number you can actually represent is 255. But there are 256 numbers that are representable by means of n bits. So in general, in 2's complement number systems, the range of numbers that you can represent by n bits is all the numbers. You can represent them from minus 2 raised to the n minus 1 to 2 raised to the n minus 1 minus 1. So can you think very carefully about this? In my mind, it's a bit tricky. All right, talking about the range of numbers. So if you've got 8 bits, you can represent minus 120 all the way up to 120 plus 128 minus 1, which is 127. So what about adding and subtracting using 2's complement numbers? Well, obviously to add 43 and 83 in decimal is as easy as that. 8 and 3 is 11, carry 1, carry the 1. 8 and 4 is 12, add 1, you get 13, 1, 3, 1. And to add let me just make this a little bit bigger. So to add these two binary numbers, you get this number. All right, this is normal. I'm not assuming this is a 2's complement number. So I'm just adding 2 normal. I mean, check it. Just check that I'm not making mistakes here. Right. So to enable a computer to carry out subtraction involves the method of converting the number to be subtracted into a negative number and then add it to the number from which it is to be subtracted. So for example, if you want to subtract 13 from 20 in decimal, it's equivalent to adding 20 to minus 13. So the binary representation of 20 is this, and again you need to check that. Is that equivalent to decimal 20? I think it is. And the binary equivalent in 2's complement arithmetic is 111110011. And you might say, well, how come? Well, use the technique. First of all, start with 13, then use the rule I've just given you to convert a number into 2's complement. You start with the least significant bit, work your way left. When you come to the first one, leave it alone, but then flip all the other bits, and you will get this. It's a negative number, and that is going to, when you add minus 128 to the decimal equivalent of that, you will actually get minus 13. So just check that out. So adding 20 to minus 13 is the result of adding these two numbers together, which is 000001111. And converting 1111 back to decimal gives you 7. And there's a bit of overflow here because when I'm doing the addition, I get more bits than I should really can handle. That I get what's called an overflow of bits, and I can ignore those. So converting these four digital bits back to decimal gives you 7. And that is correct. Take away 13 from 20 is indeed 1111 here. Okay. So believe it or not, we've covered a fair few ideas in a relatively short space of time, but I do need you to be able to do that, to do these operations. And as budding computer scientists or engineers, it's very important that at least you know and understand binary numbers and different number bases. So let's get rid of that and confirm, and so for the last part of the session, I want to just address the topic of Boolean algebra again, and the outcome of that is that you will understand what a full adder is and how to construct hardware from the Boolean equations. So I'm just going to take a very, very short break whilst I have a drink. So let me try and remove this. I'm not quite sure where the presentation is. Okay, so it's a continuation of the work that we did last week, and you may have already had a look at this, and if you have, and you should have, because I set some assessed coursework based on Boolean logic and De Morgan's law. And I'd set you, this is homework, so I hope you've attempted this, or you're about to attempt it quickly. So, in the very first topic I gave at the beginning of the year, and it's in the architecture documentation, we actually had a computer instruction that resulted in adding two unsigned integers together. And my question is, how does hardware or pure logic perform this operation? Well, I'm going to start off with a simple logic description and circuit that actually results in adding two bits together. So to add two binary integers together, electronic circuits called adders are used. And these are formed from combining logic gates together. And adders are commonly found in ALUs. And there are two main types, half adders and full adders. And what an adder does, what a half adder does, is to take two inputs and add the inputs together. And in the case of a full adder, the adder actually takes into account a carry bit that is passed to it, and it will generate its own carry bit if necessary. And that carry bit will be connected to the next half or full adder as appropriate. A carry bit is needed if the result of the sum requires another digit to correctly represent it. So adding a 1 and a 1 gives a 1, 0. So the carry bit represents the need for the most significant bit to be 1 to represent a 1, 0. A half adder computes the value of the sum of two binary bits and the value of the carry bit. And here it is. This is the circuit for a half adder. And I think you will agree, after we've discussed it for a minute or two, that it gives us exactly what we need. So I've got two inputs, A and B. So each input can be either 1 or 0 or both. And the exclusive OR gate will actually represent the sum of adding A and B. So if I've got a 1 here and a 1 here, the value of S, output S, is going to be 0. And that is the result of adding 0 and 0. But I also need to generate a carry bit. So from A being 1 and B being 1, I want to generate an output called C. And that's going to be 1. If A is 1 and B is 1, the sum is 0 and the carry bit is going to be 1. I've got 1, 0 in other words. And how do I do that? Well, it's just simply the result of adding A and B. ANDing A and B. You AND A and B, if both are 1, the output C is going to be 1. And if you reflect on this, this is exactly what we mean by adding two bits together. And I'm going to represent the addition by 2 bits. You know, the carry bit might be 1, it might be 0. It depends on what the two inputs A and B are. So just to explain it a little more, if A is 1 and B is 0, S is going to be 1, and there's going to be no carry bit. The carry bit is going to be 0. It's exactly what we want, what we're looking for, what we hope to specify. So here, I mean, the interesting thing is that you see a little bit of logic calculating or serving as the function of adding two two bits together. And to me, that is quite interesting. You're using pure logic. You're using pure logic to compute the result of adding two bits of information together. Two bits of information together. And the other thing I'm inviting you to look at is that, okay, well, you probably already know that this is the symbol for an exclusive OR gate. This is the symbol for an AND gate. It's a physical item, and this is a physical item. I can actually hold one of these in my hand. It'd be very, very small. Or I could actually manufacture a circuit with millions of these logic gates on them. So I'm talking about hardware. So I'm inviting you to think about the transition from a logic description of a circuit to the actual physical implementation of hardware here. Right? So let me just go back a bit. The truth table for the logic circuit is easily producible, and all we need to do is to consider all possible values of A and B, 4 combinations, permutations if you like, 0, 0, 0, 1, 1, 0 and 1, 1. And it's easy to see that, for example, A, B is going to be, if AB is 1, 1, then S is 0 and C is 1. And if A and B is 1, 0, S is 0 and C is 0. And with this result for same result, excuse me, I'm just going to have to delay things for a moment. So please bear with me just for a couple. Hi, I'm back again, so I apologise for that, but it's something I had to do. Um, so little test, little exercise. Write these values up in a truth table. Well, it's not, it's very easy to do. You get something, you get an abbreviated um, truth table looking like this. But of course, if you refer back to the circuit, um, you should have a column representing the result of exclusive ORing two values A and B, and you should also get another column representing the result of ANDing those two values. Right, if you were asked to provide a truth table, you do get that, but this is just a summary truth table. I mean, you've got the values of C and S, the carry bits and the sum. So a full adder takes into account the carry bit um, from the addition of two bits on the right hand side. For example, if the two digits to be added are 1 and 0, but the carry bit from another uh, half adder is 1, then the full adder will give 0 and output a carry bit for the two bits to be added on the right hand side. So let me just show you what I'm talking about here. So I've got a carry bit coming in from a previous unit. I've added two bits and I'm now passing a carry bit to this particular adder for the second bit. And it's more complicated because if you have a look at it, I've got two exclusive ORs, and to calculate the sum of two bits A and B, I'm first of all going to first of all exclusively OR A and B, and then with the carry bit, I'm going to pass that to another exclusive OR, and then output S. So for example, if A is 1, and B is 0, and the carry bit is 1, then by adding 1 and 0 I get 1 coming out here. And if I've got a carry bit of 1 coming in from my neighbour, then I'm going to exclusively OR that, and I will actually get a 0 because that's a 1 and that's a 1. And the circuit, the logic for computing the carry bit is simply, well, if the result of exclusively ORing A and B is 0, I want to AND that with the incoming carry bit, which might be a 1, might be a 0. And that will give a 0 here in this is an OR gate, and the carry bit out, the carry signal will be 0, but if both A and B are 1 and the carry bit is 0, I'm going to AND those two signals A and B, and I'm going to OR a 0 because they've got a carry bit here and it's 0, so this AND gate is going to output 0. So I'm ORing a 0 with a 1, and therefore the carry bit is going to be a 1 here. And that's correct if you think about it. Okay, so I've given you the circuit, and little note about the creation of a full adder from a half adder, the construction. If I've got 10 half adders, I can join them all together. So I can chain them together. So one half adder is going to output a carry bit to the next half adder, and so on and so on. So full adders take 3 inputs, which are the 2 binary digits to be added plus the carry bit from the previous addition. And the outputs the output is the sum of all that plus the carry bit. Notice in the logic diagram above it should be that carry in represents the value of the carry bit at the start of the addition, and carry out, C out, is the value of the carry bit at the end of the end of the calculation. And C out from the first adder becomes C in on the second addition, and so on. So what I'm talking about here is a circuit that looks a bit like this. I've got a full adder here, in the sense that it's taking into account a carry bit input from a unit up here, and it's going to generate a carry bit output, which is going to be fed back into the next adding unit. And if you consider this, you will realize that this is how you could, if you wanted to, add two 16-bit numbers together using logic alone, or if you converted the logic into equivalent logic gates, you could do the addition in hardware, i.e. very, very quickly indeed. Actually do the calculation. I mean, you don't need a program to do it, you've got hardware to do it all for you. And I'd like to say just a couple of words about the Sheffer stroke. There's something called the Sheffer stroke, and it's one of the 16 definable binary operators, or connectives as they're called, of standard logic. And the Sheffer stroke is represented by a vertical bar, and the linguistic expression whose logical behaviour is presumed is modelled by the logical connective. So again, the linguistic expression whose logical behaviour is presumed modelled by this logical connective is the truth function or phrase not both, from which the name not and originates. So in other words, A vertical bar B is equivalent to not A and B. It's not and. So interestingly, if you write A vertical bar A, and that means not A nor A, you're actually talking about not A. Right? So you can define negation, or the not operator, in terms of the Sheffer stroke. And I think this is still current. This YouTube video, if you want to have a look at that, I think it's talking about the Sheffer stroke. But in addition, there's something called the Nichol stroke, and you could find out a little bit what functionally a Nichol stroke is. I mean, the really interesting thing is that using the Nichol stroke or the Sheffer stroke, you can define all the other logical operators. In other words, you can define not and or and if then and so on. I mean, you can just use one primitive logical operation to define everything else. And perhaps another possible universe, all circuits will be built using just the Sheffer stroke. I mean, maybe there's someone has got a technique for implementing this operation very easily in large quantities, and very, very inexpensively. I mean, that would be quite a cool research topic, I think. And Mustafa, are you still here? Because I'd like to just talk a tiny bit more about logic.
Yes.
Hi, can you tell me what the following? Uh, can you give me the logical expression for the following expression? And the expression I'm interested in is for everything in the world has a particular size. Everything in the world has a size. Could you represent that purely logically? I mean, I don't think you're going to quite understand my question, but
Yeah,
but
I have no idea.
okay. Well, what I'm actually asking for, can you re-express that sentence in terms of logical operations like and or and so on? So that the sentence is, it's a proposition. Everything has a particular property, and in this case, everything in the world has the property of having a weight. I mean, would you be able to express that in terms of ands and ors and nots?
Okay, I will look at it. Okay. Now or for homework?
Well, I just don't, if you can think of, I mean, I mean, I mean, I can actually give you an idea. I mean, you should be able to re-express what's called a universal quantification, because you're talking about everything, everything having a certain property, in terms of ands. In other words, you can actually say, look, everything in this room is owned by Christopher Kinberg. It means that the computer I'm sitting at is owned by Chris Kinberg, and the book that's sitting on my table is owned by Chris Kinberg, and the cup of tea that I've got on the table is owned by Chris Kinberg. In other words, I could re-express this statement, this proposition, purely logically, and I can actually represent it by means of a conjunction of sentences like this has the property, that has the property, this has the property, that has the property, and. And so what I'm asking you to take on board is that logic has a deep reach. It pervades a lot of what we we think about and how we think about and how we compute things. For example, if I wanted to disprove everything in this room belongs to Chris Kemberg, all I'd have to do is to find a single example of something not belonging to Chris Kemberg. That would be, disprove that general claim. And the other thing I wanted just to say a little word about is what's called. Let me write these two terms down. The first um, thing is, let me just write this sentence. All things have some property, have a property P, and that's called a universal quantification. No, I've spelt that badly. Quantification. Okay, and the other thing I wanted to mention was called an existential Existential quantification. Not spelling this, my spelling is awful at the moment. And an example of an existential quantification is simply this: there is something that has the property P. Let me write that capital P. And so the first can be re-expressed Okay, so I've introduced you to two things: existential quantifier, which corresponds to the universal quantifier, which corresponds to something like everything or all things have a certain property, and the existential quantifier or existential quantification, which means there is something has the property. And the first quantifier or quantification can be re-expressed using ands, nothing but ands. And the second quantification can be re-expressed using ors, logical operation of oring things, like either either this object has the property or this other object has the property. At least one of those objects that I'm talking about has the property. And that means something has the property. And the reason I'm talking about these two things is that part of computer science involves AI, and some AI systems involve knowledge, what are called knowledge bases, and you can represent knowledge in terms of logic, pure logic expressions, like London is to the north of Brighton, and you can represent knowledge also by quantifiers, like you can say all numbers less than 10 have such and so property. And together you can represent the entirety of human knowledge using logic expressions. And we've covered a few of those logic expressions, which you probably obviously already familiar with, because you use the logical operators every day in your life. But some systems represent highly intelligent systems, and they are knowledge based. Their responses depend on what knowledge they can turn. So, for example, you might have a knowledge based system that doctors use, and in the knowledge base, you're having thousands of facts and properties about the human body and its function, and a lot of information about drugs and medication that might be used to treat an illness, or you might even have a lot of expertise needed to perform brain surgery in the desert. Maybe you're on your own with a partner, and you can actually interrogate the expert system to find out what's wrong and give a diagnosis, and maybe even treat the person. Maybe reawaken them if their vital functions are disappearing. Anyway, I just wanted to end up on that. So we've covered a fair amount of different things today, and hopefully the materials I'm going to send you will clarify um, some of the things we've been talking about. And I mean, I think I've got slightly confused over one or two binary additions, but I'm not too worried about that. And you've got all the materials that you need if ever you want to take these things further. So I don't know whether you have any questions or comments, but this is our last session. And the only comment I want to make is that I will be setting yet another, and it'll be the fifth. It'll be the fifth assessed coursework at the latest by tomorrow night. But I'm going to keep it easy. Don't worry. It'll be quite straightforward. I mean, you've done enough work. You should have done five, Mustafa. One I gave you before on the last session before exam week, and I've given you this is going to be the fourth piece of work I've given you since the end of exam week. Um, okay, but don't worry about that. In your case, I'm quite happy to prepare an assessment on the basis of say three or four different courseworks, and I can always average them and give you a good mark. So don't worry about that. Just keep working hard. You know, we were at it. Were we talking last night on WhatsApp? Is that right? Can't remember.
Yeah.
Yeah, okay. So I'm going to finish early today because I've really got nothing else to say. But if you want to make a comment or ask a question, please do. But you know you're welcome to ask questions at any time using WhatsApp or email.
Yes. Okay.
So you're happy-ish.
Yeah. Yes.
You're not stressed or anything like that.
No. No. I'm okay.
All right. Well, you've done very well. So keep in touch, and I'm sure we might have the opportunity of talking on WhatsApp very soon again. And there's no reason why you shouldn't just call on me at any time. Okay. Okay. So I'll say goodbye, and I'll put the materials up very soon onto Pharos, and I shall put um, two recordings up as soon as possible. Video recordings. All right.
Thank you so much.
Bye bye.
Bye bye.
You are currently the only person in this conference.